my great pleasure to give this public lecture. Let me first thank Endo-san and Mino-san for organizing a very nice workshop that has just concluded. And with this public lecture, I want to give you a brief overview of the use of quantum field theory in theoretical physics. Since the public lecture part of this talk is going to be at the elementary level, but you will see some more technical materials closer to the end of the talk. So first, the plan of my talk is to first go through the origin of quantum field theory, and then very briefly mention the use of quantum field theory in its original goal, which is application in particle physics. And then I'm going to give you 3 examples of the use of quantum field theory in condensed matter physics. And I will conclude after that. I will give a brief conclusion. Okay, so before the revolutions that give us quantum mechanics, classical physics can be thought of as a building that built on 2 pillars. One is classical mechanics that is summarized in Newton's law of motion, and Newton's law of gravitation. And the second pillar is the theory of electromagnetism that is summarized in 4 Maxwell's equations. Newton's law governed the motion of, for example, heavenly body. So you have an equation that say how these planets or stars move in space according to Newton's equation, which give us the acceleration as a function of force, also determine the force acting on each particle. Somehow it's cut off. I'm not sure. Let me see how to make it smaller. Yeah. A Maxwell equation, on the other hand, govern the evolution of the electric and magnetic field. So these two parts of classical physics looks quite different from each other. So here's the picture of the field lines. I think this picture was made by Faraday himself by using ions. So the fields live in the whole space. So there is a great discrepancy between the number of degrees of freedom contains in a particle and the number of degrees of freedom contains in the field. In order to specify the state of a classical particle, we need to specify its coordinate, x, in 3-dimensional space, that 3 numbers, and then its momentum, which is p, or velocity. So 6 numbers completely determine the state of a classical particle. On the other hand, in order to specify an electric or magnetic field, we need to give the value of the field at every point in space. So the electric field is a function of x, and the magnetic field is a function of x. So actually, there are 6 functions of coordinate x that amount to an infinite number of numbers that we need to give in order to completely specify the initial condition, for example, for the Maxwell equation. So fields contains much more information, or we say much more degrees of freedom than particles in classical physics. When quantum mechanics was born 100 years ago, with the work of Heisenberg and then later, slightly later, Schrödinger, it was first motivated by a desire to understand a system of particles. like the hydrogen atom, which is a simple system of a nucleus, protons, and electrons interacting through a Coulomb potential. So Heisenberg works how to go from classical mechanics to quantum mechanics. So in Heisenberg picture, particles is still described in a similar way as in classical mechanics. We can use x and p to specify a particle. The only thing that is more complicated in quantum mechanics is that the momentum and the coordinates do not commute with each other. Xp minus px is equal to minus IH bar, where H bar is the Planck constant. But using this rule of quantization, we can take the starting point of a mechanical model of an atom, for example, it's Hamiltonian, and then treat x and p as operators that do not commute with each other, and then derive the properties of the hydrogen atoms, in this case, the spectrum of the hydrogen atoms. So in this way, we, Heisenberg and Schrödinger managed to reproduce the result that was first proposed by Niels Bohr in his model of the atoms. In Niels Bohr models, there is a rule of quantization that wasn't clear how to fit it within the framework of classical mechanics. But with the new quantum mechanics, people started to have a systematic way to treat all the system that is built out of point-like particles like a nucleus and electrons. The new rules of quantum mechanics also explain the previous suggestion that particle can also be described as waves. Energy and momentum of a particle, for example, correspond to the frequency of and the wave number of the wave. So E is equal to H bar omega, when omega is a frequency, and P is equal to 2 pi to H bar K, where K is the wave number of the wave. But this wave is just in quantum mechanics, this wave is a way to describe the probability distribution of a particle. This wave is not a field. The necessity to introduce a quantum field appears when one tries to understand the transition between different energy levels of hydrogen atoms. The Schrödinger equation only tells us that there are different discrete energy levels of the hydrogen atom. But we know from experiments that when we put an atom in an excited state, then after some time it will emit a quantum of electromagnetic fields on the photons and goes to a lower energy state. In order to compute the rate of such a process, one has to be able to treat quantum within a quantum framework, the electromagnetic field as well, and that's that was the first, I think, case when one needs to quantize the electromagnetic field. That when it was done, we can understand and compute the rate of emission of a photon by an excited atom. So in this stage, at this stage, the electrons are still treated as particles, and the electromagnetic field as a field. So there is still a discrepancy between matter and fields, like these particles and fields. But in fact, very soon people realize that even the electrons have to be described, has to be treated as a field in a more complete theory of nature. And that comes with the work of Dirac. In 1928, Dirac wrote down a relativistic wave equation. He was trying to generalize Schrödinger equation into some equation that is consistent with the theory of special relativity. So he wrote down his equation, the Dirac equations, And he discovered that this equation described not only the electrons, but also another particle as a consequence. It's a consequence of this is the only way to sensibly interpret his equation is to say that it described not only the electrons, but also a particle that we now call the positron. Actually, first Dirac thought that this particle, since it has to have a positive charge, should be identified with the proton, which is the only elementary particle with charge +1 that is known at the time. But soon it becomes known that this proposal should not work. I think Oppenheimer was one of the persons who pointed out that the hole and the electron should have the same mass. And so this particle was then proposed. Dirac and other people came to the conclusion that this particle with positive charge should be treated as an independent new particle, the positron, which was later on found in cosmic rays. So the Dirac equation has the origin in an attempt to generalize Schrödinger equation to relativistic case, but an attempt to interpret the Dirac equation in the same way as the Schrödinger equation led to a nonsense, which is negative probability. Physically, we now know that this is related to the fact that the full theory should have both electrons and positrons. So we cannot have a theory that contains only electrons. If we have a state of some physical system that has one electron, and if these electrons interact with something, if there is enough energy, there is a probability that this electron would produce a pair of electron and positrons. One electron can become one electron, and a positron, one electron and two pairs of electron and positron. So in the real world, because Einstein told us that energy can become mass, the number of particles is not conserved. That's the usual framework of the Schrödinger equation is to write down an equation that describes a system with a fixed number of particles. Such an approach would not work in relativistic quantum mechanics. So the theory that we should aim for should be a theory that can describe not only a single electron, but a general situation where there could be any number of electrons in any number of positrons. And it's known now that the correct description of electron and positron is through something called the fermionic field. A fermion field is against a concept that allows us to describe not only a single electron, but a more complicated system that has any number of electron and positron. And here you see that the fact that it's a field made it possible to do so. In a field, there are much more degrees of freedom than the coordinate of a single particle. So in one field can describe not only a single particle, but a state that contains any number of particles or any number of antiparticles. Now, particle physics is completely based on field theory. In this book by Alexander Polyakov, a Soviet physicist, he wrote that we have no better way of describing elementary particles than field theory. The standard model of particle physics is one of the examples of such a field theory, and it describes all known elementary particles very well. This is the Lagrangian of the standard model in a very abbreviated form. This simple theory with about 2 dozens of parameters can describe a very large number of experimental data. But particle physics is not the only place where quantum field theory has made an impact. I'm going to go through 3 examples of the application of quantum field theory in condensed matter physics. The first example is the description of the so-called Nambu-Goldstone bosons. And then I'm going to tell you about graphene, physics of graphene, and the use of renormalization group, which is a technique from quantum field theory. And then, as a third topic, I'm going to very briefly tell you a story of fractional quantum Hall effect and the use of field theoretic duality in this system. Okay, so the first example that we're going to consider is phonons in the solid. So if you consider a solid, a crystallic solid, it can be represented as a lattice of atoms. So atoms interact with each other, and in minimizing the energy, it wants to arrange themselves into a lattice, like the one drawn on this slide. And phonons are the quantum of sound wave that are the fluctuations of this lattice. So if we shake this lattice, the new position of the atoms will be shifted from the old position. One particle, this atoms that's located at some point, is going to be have its position change to a new position x, going to x plus u. And so an atom its position x is displaced by an amount that is equal to u. And on in a real crystal, x has discrete values because x is the position of the atom in the original lattice. So x can be decomposed into basis vectors of the lattice a1, a2, and a3, which is then x 3 integer number n1, n2, and n3. And u is a function of this n1, n2, and n3. But imagine that we try to describe sound wave with a very large wavelength that is much larger than the distance between the atoms. Then this x can be considered as a continuous variable because the wavelength contains so many possible values of n1, n2, and n3. Since x is a continuous variable, then the displacements of the atom u is now a field. That is a function, u is a function of x. It's a field. So here you see the appearance of field theory as a very simple origin. We want to describe the state of a lattice of atoms at distances that are much larger than the distance between the atoms, and so the medium becomes basically a continuous medium. Now, the lattice of atoms, this crystal, is an example where we have a phenomenon in quantum field theory called spontaneous symmetry breaking. Let me explain the word symmetry. In this case, symmetry that we have here is one of the important symmetry is the translational symmetry. That is the symmetry of space. Not in space, all the points are equivalent to each other. There's no point that I single out. But when we have many atoms that interact with each other, we have said that they spontaneously form a lattice. When they try to minimize their energy, they form a lattice, and the lattice doesn't have translational invariance anymore. Not all points are equivalent. In fact, there are points that are singled out. The position of the atoms are singled out. So the ground state of the solid doesn't have translational symmetry, the full translational symmetry. It has some residual translational symmetry by a discrete vector, but there is no continuous translational symmetry anymore. And in quantum field theory, there is a theorem called the Goldstone theorem that tells us that if there is a continuous symmetry that is spontaneously broken, then there must be a Nambu-Goldstone boson. Such a particle must be a massless particle. That is a particle whose energy goes to zero as its momentum goes to zero. So in our example, the origin of this Nambu-Goldstone boson can be seen in a very simple way. There is a way to disturb the lattice without changing its energy. We just shift all the atoms by the same amount. Right? This can be the new state can be considered as a state where there is a sound wave propagating, but the sound wave has infinite wavelength. It's the field U is uniform everywhere, and so such a excitation of the system should have zero energy. And after quantization, we see that the energy of this mode is proportional to the velocity of sound times the momentum of the mode, and that goes to zero as the wavelength goes to infinity. So this is the illustration, one example of the appearance of the Nambu-Goldstone bosons out of spontaneous symmetry breaking, something that was first talked about within quantum field theory applied to particle physics, but now it is a theorem that is used everywhere in condensed matter physics. So, for example, if we have a magnet, an isotropic magnet, have its magnetization point in one direction in space, so that would break rotational symmetry. The Nambu-Goldstone boson that comes from the breaking of rotational symmetry is called a magnon. Magnon is also a massless particle. That is, a magnon has energy going to zero when its momentum goes to zero. How the energy of the magnon goes to zero as a function of momentum depends on whether we are dealing with a so-called ferromagnets or anti-ferromagnets. But the Goldstone theorem tells us that there is always a massless particle. So another more non-trivial example is the physics of superfluid. Superfluid also has a, for example, superfluid helium also has a Nambu-Goldstone boson, which is the superfluid phonon. But the symmetry in the case of a superfluid is a very non-trivial symmetry. That symmetry is a symmetry related to the conservation of particle number. So it doesn't have a classical, it doesn't have a classical analog. It's really a quantum symmetry that is easiest to see in the field theory description of superfluid helium in terms of a bosonic field. The symmetry is the phase rotation of the bosonic field describing the helium. So let's stop here and talk about one notion that we are going to use later on, the notion of quasi-particles. Phonon magnons and superfluid phonons are examples of quasi-particles in condensed matter. A quasi-particle is not an elementary particle, like an electron or a neutrino, but it behaves in many ways like a particle. One can visualize such a particle as a lump of energy that travel in space. That lump of energy has a finite size, but if we are interested in the physics at long distances, this quasi-particle a lot of time can be thought of as almost like an elementary particle. In the case of phonons, we can see how quantum field theory is needed to describe this phonon. When we take one phonon and then collide with another phonon, the number of phonons can change in the collision process. In the classical physics, it's related to the nonlinear effect in elasticity. This nonlinear effect in elasticity after quantization becomes possibility that phonons can interact with each other and produce more phonons. The quantum field theory as a field theory that is not tied to the degrees of freedom of a single particle, but contains an infinite number of degrees of freedom, one per point in space, is a very convenient formalism to describe such a situation. And it turned out that the theory of phonon is a quantum field theory of Nambu-Goldstone boson. Okay, so let me tell you another example where quantum field theory can be used to get a non-trivial result. And the second example is graphene. Perhaps most people here have heard about a breakthrough in condensed matter physics and material science some years ago, when people managed to take out one sheet of carbon atoms from graphite, which is a three-dimensional material, and study the lattice of carbon atoms arranged in hexagonal lattice like this, and that material is called graphene. Graphene is a two-dimensional material, two-dimensional sheet of carbon atom arranged in hexagonal lattice. Okay, so graphene is a semi-metal. So it's something that lies between an insulator and a metal. From the point of view of quantum field theory, insulators and metals are very different states. So the insulator is a state of matter that does not have any low energy quasi-particles. All the quasi, in order to excite insulator, we need to spend finite energy. So such an insulator cannot conduct electricity, because in order to conduct electricity, we have to excite a quasi-particle that can carry charge from one place to the other. So an insulator is a thing that does not have any low energy degree of freedom that carries charge. Metal, on the other hand, is a state of matter where there are a lot of degrees of freedom that can carry charge. So a metal, the low energy degree of freedom in metal are electrons that have momentum that are near a surface. So the momentum is a three-dimensional vector. And in a metal, the low energy degrees of freedom are the electron where the momentum is located on or near a surface, two-dimensional surface in three-dimensional space. It's called the Fermi surface. And this should be semi-metal, not seminar. Somehow it's must be spell check. Semi-metal has a much fewer degrees of freedom. These are electrons with momentum near certain points, as I will see in the case of graphene. In the case of graphene, there are, if we use band theory of solids, this a very standard way to do solid state physics. One see that these low energy quasi-particle in graphenes are negatively charged electron and positively charged holes near something called the Dirac point. There are a finite number 2 of these Dirac points in momentum space. So near this Dirac point, we can have electrons and holes. And these quasi-particles are described most easily by Dirac theory. But with the modification that there is no mass for these quasi-particles, and the speed of light is replaced by the speed of this quasi-particle, which is 300 times less than the speed of light. So Dirac theory makes a revival in condensed matter physics with the advent of graphene. I think before the discovery, the experimental discovery of graphene, Dirac equation is usually not part of the standard education of a condensed matter physicist, and now it basically very essential part of education of a condensed matter theorist. So this is this electron and positron are described. But the electrons, there is no positron, but the positron is like a hole in a band, in a field band. Now, the correct description of graphene, when one tries to introduce interaction between the electron and the hole, is a theory similar to quantum electrodynamics, but in mixed dimension. The electrons and the holes live in the two-dimensional sheet formed by these carbon atoms. So they have an atomic size, but at the at long distances, we can think about a sheet that has 0 size. So these are our electron and positron, and they interact with each other through electromagnetic field. But this field lives in 3 dimensions. So the field lines of the Coulomb field between the two of these particles would goes into the 3rd dimension. So this reminds one of some some scenarios that has been discussed in particle physics, trying to speculate what lies beyond the standard model. Some people speculate that our standard model lives in a 3+1 dimensional membrane that is immersed in a space with higher dimension. And such a picture is called the Bringworth scenario in particle physics. Graphene realized a very simple Bringworth scenario where the matter field, this particle, electron and positron, the electron and holes, they live in 2 dimensions, but the particle they exchange, the photons, can go into the 3rd direction. So now this is a theory that can be treated as a quantum field theory. And there is a very interesting prediction for graphene that has been made using the method of renormalization group. That is one method in field theory that was developed in 1950s for quantum electrodynamics. And that using renormalization group, one sees that the electron charge is actually not a constant in electrodynamics, but is something that changes with the length scale. In particular, if one measures the force between 2 electrons, the Coulomb's law would say that this force should be 1/r² times a constant which is E². This is the product of the 2 charges, E of one electron and E of the other electrons. But in quantum electrodynamics, this force is 1/r² times some function of r, which is the square of the charge of the electron that changes quite slowly with the distance r, so that most of the change of the force is still due to that 1/r². But in fact, there are some change in the force that is due to a very slow change of the electric charge of the electron as a function of radius. And the physical reason for this dependence of the electric charge of the electrons on the distance is due to the phenomenon of screening. That is, our vacuum is not actually should not be visualized as something static. At very short distances, around 1 electrons, we can see pairs of electron and positron popping up. And so the charge that we see when we measure the charge of the electron at long distances actually is not the bare charge of the electron. It's something that has already been screened by a cloud of electron-positron pair. And so in quantum electrodynamics, one measures the charge of the electron, which is characterized by this constant alpha here. Alpha is actually E². When we go to short distances, it goes up because we see less and less screening of these electrons. So when r is small, we should see a larger and larger charge of the electron. So this renormalization group was developed in 1950s. People see that the charge of the electrons that we see here is already an asymptotic value of this charge at distances that much larger than the so-called Compton wavelength of the electron. It's about 10 to minus 10 centimeter. At short distances, it should go up. In the 1950s, people see that it can go up to infinity, and that create a problem for quantum field theory. For a long time, people were very confused about the divergence of the charge at very short distances. But now we know that quantum electrodynamics is not supposed to be applied to such short distances. But before that happened, there are many more physical effects that would need to be considered. But now return to graphene. So now that calculation using renormalization group in graphene show that the velocity of the electron in graphene slowly changes with its momentum. When we lower the momentum of the electron, its velocity becomes larger. So if we draw the dispersion curve for the electron energy as a function of k, without using just band theory, we see this line has to be linear as a function of k. But a more accurate treatment of the problem that take into account particle-hole pair creation using quantum field theory show that as we go to longer and longer distances, the velocity of the electron becomes larger and larger. One can visualize this as the effect of the photon on the electron. Photon travel with the speed of light in the third direction. It can transfer information much faster than the electron. And so when we go with the renormalization group to very long distances, electron velocity try to catch up with the photon velocity. Eventually, it will asymptotic to the velocity of the electron, but it will happen very slowly. With realistic distance, the electron velocity is still much smaller than the velocity of light. This prediction, I think one of these quite non-trivial use of renormalization group has been confirmed experimentally. The velocity of the electron in graphene slowly changes with its momentum. Okay, so now the third example that probably I will have to describe without a lot of technical details is the quantum Hall physics and duality. Fractional quantum Hall systems are the ultimate strongly coupled system in condensed matter physics. It is a very rich system. The theoretical problem is very complicated. Experimental data are quite abundant. Here we see the use of one of the most sophisticated uses of quantum field theory. The system is very simple to start with. It's basically charged particle, electrons moving in 2 dimensions in a very high magnetic field. So here is a picture from a textbook. We think about a 2-dimensional system of electrons in a magnetic field H here, and we push the current J in one direction and measure the voltage drop in a direction perpendicular to the current. And we define the quantity called the Hall resistivity, which is the ratio of the voltage drop in the Y direction and the current in the X direction. So it's called Hall resistivity because this effect was first found by Hall in the late 19th century. The quantum Hall effect, in the quantum Hall effect, this Hall resistivity received quantized values. Basically, the values that is proportional to a combination of fundamental constant of nature, is h divided by e squared times a rational number, a ratio of two integer. If Q is equal to 1, then we call that the integer quantum Hall effect. If P over Q is a fraction, then we call that the fractional quantum Hall effect. So what has been measured in experiment is summarized in this this very complicated curve. That is, well, I'm going to explain only one curve here. So that is the dependence of the Hall resistivity on the magnetic fields for rather clean two-dimensional material in a rather high magnetic field of about 20, 30, 10 Tesla. You see here these plateaus where the values of the Hall resistivity is a rational number times the constant h over e squared. So there is a whole story, very long. There have been books written about the fractional quantum Hall effect. One can give a whole semester course on the quantum Hall effect. But here I'm going to tell you only one things that happens near this point when the magnetic fields correspond to a situation called half-field Landau level. That's in the technical terms, this corresponds to a situation when the number of electrons is exactly 1/2 of the number that needed to fill a single Landau level. Or in technical notation, mu equal 1/2. So experiment show that the half-field Landau level has a very non-trivial properties. That is, there is a low energy degree of freedom, some kind of quasi-particle that does not carry any electric charge. So the electrons themselves have charge, but these particles, they do not carry charge. They move in straight line in magnetic field. So here I show you this graph copied from a paper, but I'm going to only explain how people manage to see this particle. Basically, they measure this resistivity, one of the resistivity. I think this one may be the longitudinal, not the Hall resistivity, as a function of the magnetic field. And they see all this kind of oscillation if well, there's one thing. Another thing is that they superimpose in the sample external potential, and they see that there seems to be a particle that sometimes are in resonance, the orbit of which are in resonance with this external potential that they put in. So this minima can be identified with the case when the orbit of these quasi-particles are commensurate with the lattice, the external lattice. So extrapolating, one see that at this value, that some value, particular value of the magnetic field, the trajectory of this particle must be a straight line. You can write down the extrapolation formula for the inverse of the radius of this particle, and this inverse radius goes to 0 as at this particular value of the magnetic field. And so there seems to be a quasi-particle that does not fill any magnetic field at this value of the magnetic field, which can be checked to correspond to half-field Landau level. And the question is, what is the nature of this quasi-particle? Now, a quasi-particle, let's return to the notion of quasi-particles. Here, we have to remember that in metals, which is a system of electrons, interacting system of electrons, we have a theory that developed by Landau. And in this theory, the Landau quasi-particles can be thought of as an electron that is dressed by a cloud of electron-positron pair, similar to what we should be thinking about the electrons in quantum electrodynamics. So we have here a pair electrons that is surrounded by a lot of particle Hall pairs, and Landau showed that At long distances, the real quasi-particle is some object that can be visualized as an electron plus pairs of particle and holes. So in one textbook, they explain the notion of quasi-particle like this. This is a real force, this is like an electron, and this is a quasi-particle. And you can see some things that can identify this quasi-particle with the original particle. What are these things usually? Landau quasi-particle can have a mass that is drastically different from the bare mass of the electrons. So in metal, if there is a notion of effective mass, can be very different from the real mass of the electron. But there are two things that quasi-particle has to keep from the old particles, that is the charge and spin. The charge of this quasi-particle must be the same as the charge of the electron, because all the things that surround it are particle-hole pairs, and they have zero charge. And the spin of these particles have to be also 1/2. So the quasi-particle that, if we have a Landau quasi-particle in our system, that cannot explain the experiment, because anything that carries charge has to move in curve, in a circle in a magnetic field. But experiment tell us that at the half-field Landau level, there is some quasi-particle that move in straight line. So the quasi-particle in a half-field Landau level has no electric charge. There are some other arguments that tell us that this half-field Landau, this quasi-particle has to be a fermion, not a boson. So here you have to have a fermion with no charge as a quasi-particle. So the problem of understanding the nature of the half-field Landau level has a long history, but recently the renewed effort to explain some experimental data, some new experimental data, has motivated theorists to look at quantum field theory, and it's catalyzed new progress in quantum field theory. And this work has led to many new examples of duality in quantum field theory. Duality actually is something that was known in quantum field theory. Many examples of duality concern two theories that on paper looks very different. When we try to write down as the Lagrangian, they have very different Lagrangians, not many things in common with each other. But there are arguments that says that these two theories are basically the same, or at least at long distances have to be the same. Many of these examples can be proven in one spatial dimension. But there are examples in higher dimension, 2 and 3 dimension, 2 and 3 plus 1 dimension, which people believe to be true based on very non-trivial check. So there are usually no explicit proof of the duality. But what is also true is that most previously known examples before this body of works have been duality between theories with supersymmetry. The new duality that was discovered through what is motivated by the physics of quantum Hall effect are duality between theory with no supersymmetry. So let me show you one example. This is a most technical slide in my talks. These are examples of two theories that are believed to be dual to each other. One theory is supposed to be related or similar to the theory describing electrons, and the other electron in a magnetic field, very high magnetic field. This is A. And another theory is supposed to be a theory that describes the physics of the quasi-particles that appears in the long distance limit of this theory. So this quasi-particle is described by another fermionic field psi. But this fermionic field does not carry charge with respect to the physical electromagnetic field, but carries charge only with respect to an emergent gauge field An immersion gauge field has a zero expectation value at half field Landau level. And that means that this quasi-particle, though it carries finite momentum, it travels along the straight line. So this duality has not been proven, and there are many arguments that says it might be true, but if it is true, it provides a very nice interpretation of the experimental data. Let me conclude. The quantum field theory is a language of particle physics. It has been very successful also in condensed matter physics. This seems very well suited for many problems that usually a problem that involve a large number of particles, because fields, as I have told you, contains a lot of information, more information than the information contains in the coordinates and momentum of a single particle. And quantum field theory continues to be a powerful method used in theoretical physics. Let me mention only two other use of quantum field theory that I was involved in with some people here. Some times ago, I worked with Yusuke Nishida, who is now at Tokyo Institute of Technology, applying method of quantum field theory for cold atomic gases. And we made a lot of interesting calculations of quantities that can be then measured in experiments with trapped cold atoms. And recently, I've worked with Masaru Honko using quantum field theory to describe some nuclear system, so-called halo nuclei. These are nuclei with a very large number of neutrons. One example is carbon-22, with 10 more neutrons than the usual isotope of carbon. And this carbon-22 is basically a three-body system: two neutrons very far away, and one core of the carbon-20 at the center. So it's only three particles. It looks like that's something where quantum mechanics should be sufficient to describe. But we found that quantum field theory, there is a field theory that can be used and quite convenient to get to obtain physical properties of that nucleus. So thank you very much.